Thank you, everyone. So I'm Liron Allerhand. This is a joint work with Dr. Abed Assi, who unfortunately couldn't make it today, so I replaced him in the last minute. So we're going to talk about emotion detection from text using deep learning. It's part of a new product by Microsoft called Video Indexer, and we will talk about it and how can it be useful. We're part of an affective computing framework. Affective computing is basically emotional intelligence for artificial intelligence. We just can't call it artificial emotional intelligence because that's AI. That's impossible to say. We will use a deep learning approach to analyze emotions in text. Most of you are probably familiar with sentiment analysis. This is not sentiment analysis, this is emotion analysis. We will talk about the difference between the two. We will use, we'll look a little bit about psychological models and data sources, data sets, and then we will talk about how we did that with deep learning. It's impossible to point that way, right? Can you see what I'm pointing at? Yeah, okay. And we will talk about the difference between those traditional models and deep learning models. We will suggest our approach for capturing emotions in different text granularities and how we manage to move from low granularity to high granularity in an efficient and interpretable manner. So here's an example of emotion detection and why we want to go beyond the sentiment, not just positive, negative. So sentiment analysis will be just positive, negative, right? We can do that on several granularities, but that's all it is, positive or negative. Emotion tells us more. Is it fear or sadness, for example? That's an important distinction, but we don't get that from sentiment analysis. So we don't only determine the polarity, but also the actual emotion. And here you can see part of the dashboard of this product, and it shows you the sentiment. Green parts are parts that show positive sentiment, and red are parts that show negative sentiment, and you can also see which sentiment that is once you zoom in. I'm not talking about too much why we want it, right? Why we want emotional intelligence or automatic emotional intelligence, that's obvious. So where does that come into play? At all sorts of service operations, for example, call centers or sales centers, we want to track a client's emotions throughout the call. So we can do several things with that. We can correlate the performance of the agent of the service provider with the emotions of the caller. That gives us some analytic, what the emotions are when the call starts out, how the emotions change throughout the conversation, and also the emotions of the client are correlated with the performance of the service provider. So if a service provider, for example, has a sequence of very negative clients, or say very angry clients, that can have a detrimental effect on his performance, his or her performance. And that's something we would like to take into account. For example, that can allow managers to give that personal service provider some break time to recover from that to help make him more efficient later on. Or, for example, if they see that giving those service providers, service representatives more authority, then they can make clients happier faster. Then they can give them those authorities and have a quantifiable way of measuring this, which we know today they kind of don't really like giving representative lots of authorities, but that's also hard to measure. How will that impact the service call? And another thing is for media and entertainment. We want to enrich the videos with some semantic insights. This is where the speaker represents joy or sadness or what is happening in a video. People would often like to watch videos or media that fit their emotional state at the moment. And also this shows us something about in the social environment. So let's talk about psychological models used for emotion analysis. There are categorical models that are the more basic kind of models. They assume that there are basic emotions, and those emotions are separate emotions. So Paul Ekman categorized emotion into 6 distinct emotions. Those are base emotions: joy, sadness, fear, anger, disgust, and surprise. That's one model. And another model is by Pluchik. I hope I'm pronouncing his name correctly. That's what we see here. That in this model we have 8 basic emotions, and they can actually be correlated in that way to create more nuanced emotions, but the basic emotions are still distinct. There are other models that are called dimensional models that refer to emotions having some latent dimensions. And these models also refer to cultural differences. So emotions can be represented on several latent axes. 2 common ones are valence and arousal. Valence is pleasure in this context. I Googled it last night. So valence refers to pleasure in this context, and arousal is how arousing this emotion is. So curiosity is more aroused than for example, interest. Now let's look at the data we can start from. Of course, eventually, we want to work with real data, but to start out, we want to start with a simple POC on a known data set. And we use known data sets in order to do that. So let's see what's available, what we can start out from, and check the validity or how can we prove that this will actually work before we go gather data from clients and from real life. So those are some emotion data sets. You can take a picture if you're a data scientist. ISAER data set is a categorical data set. It has 4 basic emotions. Tails, same. Reddit data set. You can see this data set is kind of small, but this one is reasonably large. There's a movie reviews data set that has slightly more emotions. ANLI is a dimensional data set, so it has 3 dimensions. Valence, arousal, and I don't remember what that is. But so basically we have 8 corners of a cube, and we get a regression problem instead of a classification problem. And these are 2 more categorical data sets. So most data sets are categorical. And these basic emotions are available in all data sets. So we would like to start out from this. And of course, we can go to better granularity in future works. But for starting out, this is good enough. And this is also usually the emotions we'll be interested in. We are not really looking for the part of a video where the speaker shows surprise. That's not interesting in most applications, but these emotions usually are. So how will we go about it? So the first thing we want to do is introduce some semantics, some understanding of meaning into our model. And the first thing we want to do in order to do that is use word embeddings. Word embeddings are natural language processing techniques where we take very large data sets and we try to understand the meaning of words from all this data. And the way to do that is based on an ancient quote: "Thou shalt know a word by the company it keeps." In other words, if I can take one word and replace it with another word, and I can always do that, then these 2 words are synonyms, right? And if I can never replace it with the other word, their meanings are very different from each other. So if we can predict how likely is a word to appear in a certain context, we know something about the meaning of this word, or we know a lot about the meaning of this word. Some people will argue that we know everything about what it means. And this is the way word embeddings are constructed. known methods are word2vec and glav. There's the recent Elmo method, which is for contextualized word models, but we're not using that. In this case, we will use the glav word vectors. So we just get that. If you want to train a language model today, you don't have to train your own word embeddings. You can fine-tune them later if you want, but you can just get pre-trained word embeddings from the internet, and they have been trained on huge data sets. You don't have to worry about it. The word embedding itself is a vector. It's a vector of continuous numbers. Usually the length of the vector is 300. And these 300 numbers quantify the semantic similarities between the words. Another aspect of word embedding is that there is a finite size lexicon. Right? We have a dictionary which has that many words in it and no more than that. However, word embeddings we can find have 2 million, 3 million words in them, which is usually enough for almost any application we need. Also, we may always encounter a new word in inference, right? Even if we were trained to our own data set, the words used in a certain field, and etc., we can still encounter the case where a new word appears in inference that we've never seen in training. So we never want to use every single word that appeared even once in training. What we do is we replace low prevalence words with an out of vocabulary token. And when a word has small prevalence, or we've never seen it before in training, we replace it with an out of vocabulary token, which basically says this is an unknown word and refer to it as such. Okay, once we have the semantic meanings of word, we want to refer to syntax as well. And we think syntax is very important. One common method in natural language processing is once you have all the word embeddings, just average them out and you get an embedding of the sentence or the paragraph. That works well in many applications, but that's not good enough for what we need. And here's a counterexample for that. We have two sentences with exactly the same words in different order, and the appropriate emotion is absolutely different. The dangerous killer escaped 1 month ago, but recently he was arrested. We can be relaxed and kind of happy about it. And the dangerous killer was arrested 1 month ago, but recently he escaped. That's kind of frightening. So we want to be afraid about that, and we want to understand the difference between the two. So we have to take syntax into account. And the way to take syntax into account in a deep learning approach is to use a recurrent neural network. So we start out by using word embeddings to capture semantics. We use glav. It has 300-dimensional word vectors with 2.2 million words in the vocabulary. That's more than enough. And then we will feed that into our recurrent neural networks. People often use the term RNN ambiguously. So RNN refers to all kinds of recurrent neural network, and RNN cell is what we would call a vanilla RNN, a very simple form of recurrent neural network. This is recurrent neural network in the general sense, and specifically we will use LSTM, long short-term memory cells, that are the most complicated variant of RNNs which is in common use, and they work very well. They are the most popular variant and works really well for many applications, including and mostly in language. So that's the architecture of the model. We get a word, we introduce it into the word embedding, we get the embedding of the word, and this embedding goes into the LSTM, and the LSTM reads the sentence one word at a time, and in the last word we have a dense layer. So we get the representation from the LSTM after it read the last word that goes into a dense layer, a linear layer, and then we have a softmax activation to get a classification. And these are the results of the experiment. You can see the confusion matrix here. These are not percentages. These are this is actual count of the words in every bin. And we have performance per emotion. And average performance, this is average over all emotions. So that's mean averaged precision. So we get quite nice precision and recall for every emotion individually. We can also see it from the confusion matrix here. It is almost diagonal, which is what we want. And since we don't have a lot of time, I will not show you the success cases of our model. Those are plentiful and not very interesting, honestly. But I will show you where our model fails. Because I think that's important to study in every application. So we have 3 failures here. On the left, you can see the ground truth. And on the right, you can see what our model predicted in red. So the first sentence expresses anger when I discovered that the people I trusted most were talking behind my back. And the model thinks this expresses joy. Now, I'll try to explain those in a moment. Let's just read them through. Sadness, not winning a medal in the swimming contest. Joy, then the tears came into my eyes, and it just as if my mother kissed me. The last one is kind of easy to explain, right? In most cases, it saw tears. It was a very dominant feature, and it's usually referred to sadness. So that mistake is easy to explain and not very surprising. The first one, well, we don't really have a perfect explanation about it, but we want to see if we can find kind of a plausible explanation and think that it may work and keep testing on it. This product is not yet very mature. It was very recently announced. So this is one of the first versions of the model, and we will keep improving it over time. But what we think happens here is, if you read it, it doesn't look like a whole sentence. Usually you expect the sentence to have something afterwards that will express the anger. When I discovered the people I trusted most were talking behind my back, what? And the anger should come in the last part. And also, since it is an LSTM and it reads the sentence one word at a time, this part should become dominant. It's the last one. It can change everything it thinks about the sentence in this last part. So it makes sense that from a fraction of a sentence, we get this wrong labeling. And not winning a model in the swimming contest, I just think this was kind of a rare scenario where we're talking about medals. It's probably not very common, and it didn't really know what to do about it.
Not winning.
Not winning, yes. So not winning should have been better explained. I'm not really sure what happens there, but we are showing it nonetheless. Here is some information about some other experiments we tried. So we started out from a super simple random forest, just to check baseline model, very simple one. Random forest wasn't that great. Surprisingly, LSTM did better than a random forest. I'm not sure we did everything we can to tune either of them very well, because we knew we wanted to get to deep learning, but we did want to look at the baseline. Then we used LSTMs that gave us the best result in most cases. And we also tried bidirectional LSTMs. Bidirectional LSTMs use 2 LSTM networks, one that reads the sentence from beginning to end, the other one reads it from end to the beginning, and then it tries to aggregate the conclusions of both of them. Surprisingly, that did not work better for most emotions, but that worked really well for sadness. And we also tried adding a convolutional layer before the LSTM. And the convolutional layer also did not improve things very much, actually is worse in many cases. That's probably just due to the model being more complicated and not working with a lot of data. So we expect that if we work with lots of data, that will be better, but also a little pointless because we don't need this extra capacity to model emotions. evaluation. So we are comparing our model to that of a leading competitor, which I will not name. That's the advice I got from the lawyer. And he also came into my office with a club, so. But we compared it per emotion. I don't know if you can read it here. So for most emotions, our model is slightly better. We can see there's a major difference here for anger, and there's also a difference here for sadness, but honestly, none of those show a very big difference. Please note the axis, this doesn't start from 0 here. If it were to start from 0, you could hardly see a difference. The key point here is that our model is a lot simpler than theirs. They used very complicated optimization, and they tried to use context and many relationships between words, which we did not have to do. So we managed to get slightly superior results with a much nicer model, I think. Some examples, which I will skip because we don't have much time, but now you can see some labeling here. No, I will skip that. Okay, now we have a classification in a sentence granularity, but we don't want to keep it in a sentence granularity. We want to go to a larger granularity, and also we have a prior that emotions don't change right away. We don't usually get sad, happy, afraid. So there is some relationship between sentences that's similar to a CRF, if you know what that is, but we did not use a CRF here. We just aggregated them. We try to aggregate up to 3 sentences at a time by minimizing the entropy of the aggregation. So if we joined the first and second sentence and the entropy was lower, we united them, and if that increased entropy, we did not join them together. And the sliding window is in the size of up to 3, so we never join more than 3 sentences together. That's just a very simple baseline for start. And here's an example which I will also skip for lack of time. But you can see some example of the scores here, and in this case it pays to aggregate them, so we do. Okay, and here is a comparison again with our largest competitor. So this is where we both agree. The yellow slice is where we liberally agree, which is where we agree but are not exactly right, neither of us. The green slice is where the competitor is right and we are wrong, and this is where our prediction is right and the competitor is less than right. Which I think is kind of nice to have this ratio visual here. And that will conclude my talk. I will now take questions.
Hi, Ossi Mokrin from the University of Haifa.
Hi.
Hi. I've noticed that you haven't used many known things that are used in NLP and text mining and emotion mining, like bat. If you took a sentence with a bat, it is known that when you have a bat in the middle of the sentence, it sort of makes the others, if you had a positive sentence, then the rest of it will be negative. And you don't take tuples, which means that not winning would have a negative meaning, or expressions that you didn't take. So there's a lot of stuff that is known in the domain and you didn't even seem to take advantage of.
Yes, you are correct. So the answer has 2 parts. First, an LSTM model can learn this on its own, and ideally it can even learn it without the current biases in this kind of rules. So that what you're suggesting is using rule-based models, or at least partially rule-based, and this is often not necessary in deep learning models. The other part of the answer, if I'm being honest with you, is this is still an early stage product, and we will keep improving it, and maybe at some point we will test the impact of these rules on performance, and if we find they improve performance, then we will use them.
You said it's still in early stages, but I was wondering if you handled slang or typos, and if you learned how to deal with them.
Okay, so this is a word level model, so we don't handle typos, at least not in this stage. For handling typos, you usually want to use a character level model. And for slang, that will depend on the training data. So training data, as we get training data from live, from the actual product, we can handle more current slang. The slang in dataset is always past slang. So it's not very efficient to try and model it from a data set. We will try to do that. It will also happen naturally, and also in the actual product, this is integrated with the tone of voice. So we will get some feedback from that with the tone of the speaker. And we will get labels from that and integrate it into the product.
You talked about several core emotions. Have you given any consideration to an aggregated model where you try to take several emotions and bind them together based on their prevalence or their statistics?
I'm not sure how would you aggregate emotions. Do you mean every sentence will have
60% joy, 20% fear? How do you relate to that?
Yeah, actually, that will be trivial to do in this product because we use a softmax, so it actually gives us that. It gives us 30% joy and 70% fear, but that's not very interpretable and also very confusing to the end user. So we are not using that, we're using the most dominant emotion.
Did you try to do it from long text?
Long text?
Yeah, large, sorry.
No, so we did not train it on large texts. The texts we train it on are sentences, not paragraphs even, and the aggregation is done with the entropy-based method I've shown you. By the way, this method is also, we applied for a patent for that. So it's already been submitted, I can talk about it. But we have not trained it on longer texts initially. It's also very hard to find labeled data for that. And even if we had labeled data on a paragraph level, then we could not use it to give the client a sentence level granularity. So we want to use it on a sentence level and aggregate from there.
In the algorithmic perspective, is there any difference between emotion analysis and sentiment analysis?
Well, there is some, but not on a very basic model. So if you're doing something very naive, it's all the same to you, you're just doing classification. But for example, there are word embeddings that are meant for sentiment analysis. They are optimized for that, and you will get better performance with them. However, if you try to use them for emotion analysis, it will probably not work because it's meant to compress information as efficiently as possible to just get a sentiment, which means it probably discards any difference between fear and sadness. So if you're trying to really optimize your models, these kind of differences will come into play.
You have shown that different models have different ability to predict different emotion, that some models are better for specific emotion while other for the other emotion.
Yeah.
Do you have a way to explain why this is happening?
Well, honestly, I don't think we should explain it at this phase because the dataset is not large enough to be sure that this is an actual pattern. It could be that this is just some spurious correlation to the data. However, if we do find this pattern to keep occurring in large data sets, we probably should explain it. You could try and explain it by saying the size of context that matters. Sadness, for example, could depend on larger contexts, or it could depend more on things that came before some keywords than the things that came after them. And one-directional LSTMs are less good at modeling that. When we saw that the convolutional neural networks helped, that probably means that the vanishing gradients were more of a problem. So you could try all those kinds of explanations, but honestly, it's not really fair to do that at this point.
Let's thank Liron again for the great talk.